Hi everyone and welcome back to PrepFusion. I am Anish and today we will start with the lecture 34 of our electrical machines subject. So today we will discuss about characteristics of DC series and compound generators. In the previous lecture we had discussed about the DC separately excited and the DC shunt generators. Also we will discuss about the assignment 10 solutions. So one question that I did not show you in the previous lecture that was related to this concept, right? This IARA and this. So we will try to decode this question so that we understand the characteristics of DC shunt generator even further to a higher level. Okay, this is the question that I will solve. So I want you, all of you really want you to try this question out. So whatever concepts we have learned in the previous lecture, please pause the video. Please pause the video now and please try this question out. Okay, please try this question out. Okay, now, yeah. So first I will do this, then we will discuss about the characteristics of DC series generator, right? So let's read this question. A shunt generator is provided with its characteristics curve, that is EG versus IF and VT versus IL, that is the load characteristics, external load characteristics and the this open circuit characteristics, right? So determine the short circuit current, the maximum load current, the terminal voltage corresponding to the maximum load current. Okay, so basically maximum load current is here, right, where the load current will be maximum. The terminal voltage I have to find out, that is VTM. So I will copy this graph. Okay, and let me first study this graph. Okay, let me first study this graph. Of course I will slowly go into it, right, don't worry. So when these kind of question comes, right, it's kind of a waste of time if you study the graph completely. You just went ahead with the question, go ahead with the question, see what data points they are asking, then you go into the graph and see from where you can find those data points. Okay, so let me first copy this graph. First I will not study the graph. First I will just write down what do I need to find out. Okay, so I need to find out the IL maximum and the short circuit current, right? So what is short circuit current? This is the short circuit current, correct? This is the ISC. What is ISC equals to? In the previous lecture we had discussed short circuit is the condition where basically if I just copy my DC shunt generator, short circuit is the condition where the load will be short circuited. So load here is simply short circuited. If load is simply short circuited, that means the terminal voltage VT is simply 0. That means here the current will be 0 amperes, right? So if here the current is 0 amperes, the flux will be only phi residual. So due to phi residual, I will have some residual EMF, E residual. And what will be the current in this loop? Because here the current is 0. So this is just like a series circuit. So current will be E residual by RA. It will be E residual by RA. So this is the first data point that I need, right? Because I have to find out the short circuit current. To find out short circuit current, I will need E residual and IA. Is E residual provided? What is the residual voltage? Residual voltage is when the field current is 0. What is the EMF generated? I can observe, yes, when the field current is 0, they have given me this residual voltage. So this is my residual voltage, E residual. So E residual I know, that is 20, but RA I still don't know. RA value I have to identify. So how will I identify RA value? How will I identify RA value? So here, how do I know what is RA? So one thing I observe that this is the point that is touching in this graph right here at this point. This point is touching here and corresponding to this, the field current is this, right? So this is what point? This is actually the point where the load current is 0. Here the load current is 0 amperes, correct? So this is what? This is the open circuit voltage. So this voltage is the voltage where my load is open circuit, that is there is no load connected. So IL will be 0. So there is no load connected. So here IL will be simply 0. IL will be 0 amperes. So then whatever current will flow through the armature, same current will flow through the field, right? And one thing we know, if IL is 0 amperes, this is my VT, right? and correspondingly, okay, they have given me the corresponding EG value. They have given me the corresponding EG value. What is the corresponding EG value? Okay, so what is VT equals to? Actually, VT is equals to 250 or EG plus IA RA. Now assumption is, as the, now what is the armature current? Sorry, not plus, so it will be minus, right? It will be minus. So what is the armature current? I know that during this open circuit low, right, the current, armature current is 2 amperes. Why? Because the field current and armature current will be same, because the load current is 0 amperes. So actually, although VT and EG will not be equal, but you can observe that in the graph they are equal. How is it possible? So basically what we assume, because we already know that RA generally is very low value. Okay, RA is low, and IA in this case, in the open circuit condition, is very low. What is the IA value here? IA value is 2 amperes, right? So if IA is 2 amperes, IA is also low. That means my IARA will be very low, right? Negligible. So I can roughly say that my EG will approximately equals to VT. Approximately my EG will be equals to VT. How else can you understand this? So one more thing to understand this is that my VT is equals to what? VT is equals to, basically it is just a voltage divider circuit, right? So EG is getting produced here. It will be divided between RA and RF, right? So VT is equals to, it is just a resistive divider, RF divided by RA plus RF into EG, correct? And again the same thing, right? Same approximation, that roughly I can say that RF, the field shunt resistance, will be much higher, much higher than the shunt like armature resistance. So we can roughly neglect this. I can roughly say VT will be equals to EG. Okay, that's why here the graphical points are matching exactly here. Okay, it is 250 here and 250 here as well. So now can you find out what is the shunt resistance? So what will be the shunt resistance? So I know what is my EG. EG is given here 250, which is roughly equals to VT only, and I know my IF current. IF is 2 ampere from the graph. From the graph they have given me IA or IF current is 2 ampere, right here. So from here, can you find out the shunt resistance? Yes, you can. Your RSH, RSH will be equals to VT divided by IF. So VT is 250, IF is 2, so it will be 125 ohms. So this is the first data point that I am able to find out, that is the shunt resistance. But actually this was not required because I needed RA. So how will I find out RA? To find out RA, the next data point will help us is this one. If I observe that they have given me the current, load current, that is 18 ampere, and for this corresponding load current, the EG voltage they have given me. This is not the VT, right? VT might be something else, but EG voltage I know corresponding to 18 amperes. So I can use this simple case KVL, that I know. All this I am doing for the first solution. Second solution will be much easier. I mean, second part will be much easier. So I know this equation, again the same equation, that my EG will be equals to VT plus IA RA. So I know what is my VG. So I know what is my EG. EG is 200 volts here, right? 200 volts here, and IA is 18 amperes. Sorry, IL is 18 amperes. So correspondingly field current they have provided me, no field current has been provided. So how will I know IA then? So I will not be able to find out IA. So IA is equals to what? IA is equals to IL plus IF, correct? IA equals to IL is 18 amperes plus IF I don't know. I don't know the value of IF, right? So that is a problem to me. Okay. Now what else do I know? Correspondingly, one more information they have given me. What is the another information? So one more information that they have given me is this length. Okay, if I see the graph, I see that this line, where this is tangent to the graph, and this AB line and CD line both are parallel to each other, and this AB line is tangent to the graph at the same point IF, same field current point, right, where this is passing through this straight line. This straight line is the graph for the, what is this graph? If you remember, what is this graph? This graph is, if you remember, this graph is basically the equation that is uh, this graph is the equation Eg equals to how do I write it? Ef into Rf, right? If into Rf plus E residual, right? This is the graph. When If is 0, I have E residual voltage, and this is the graph. So this is this graph, right? Eg is equals to If into Rf plus E residual. Okay. So I know Eg here at this point. What is the Eg value? Eg value is 200 volts. I know E residual, that is 20. Will I be able to find out the If current? Because I know Rf. So If current will be from here. So Eg equals to If into Rf plus E residual, correct? So from here, let me color this in pink. From here, I will be able to find out my If current, right? So If current here will be equals to Eg minus E residual. Eg in this case is 200 volts, correct? It is 200. 200 minus E residual is 20 volts. E residual was 20 volts. So 200 minus 20 divided by 125. So this is 180 divided by 125. 180 divided by 125, 1.44 amperes. Okay. So from here I can directly say what will be my Ia current. So Ia current will be 19.44 amperes. Okay. So Ia current is 19.44 amperes. Now one more information they have given me. What is the other information? This is the other information, right? So I know this will be the corresponding stable value of Eg, right? Because like this is the equation of the straight line, okay, but my corresponding Eg, stable value of Eg is what? Corresponding stable value of Eg will be this point, right? Because it will further increase, it will be this point, and this is what? This is the extra additional drop, that is the IARA drop, that has been already discussed in the previous lecture here, right? Extra additional drop, IARA drop, right? So this drop is known as the IARA drop, whatever is the armature current here. IARA, which if I see these two lines are just parallel to each other, correct? Because this will be the stable point, these two lines are just parallel to each other. So this distance will be same as this distance, and in the question they have provided me that along x-axis 1 millimeter is 1 ampere, along y-axis 1 millimeter is 1 volt, and the distance of m and m is 30 mm. So what is the unit? It is 30 volt because it is along the y-axis. So they have given me the distance m and m. So I can directly say that my IARA from graph magnitude of Mn will be equals to Ia into Ra. So Mn is 30, Ia is supposed to be 19.44 into Ra, right? So from here my Ra comes out to be 1.543 ohms. Okay, this is what my Ra comes out to be. So I got my Ra. Now will I be able to find out my ISC? Yes, very easy, right? ISC will be E residual upon Ra. So ISC, E residual is 20 upon Ra is 1.543. So this will be 12.96 amperes. This will be the short circuit current. So this is the value of the short circuit current, 12.96 amperes. Okay. Now let's move on to the second one, that is the maximum load current, and that maximum voltage corresponding to the maximum load current. So when does the maximum load current will happen? So one more point they have given me, that is the developed voltage in the maximum load current, and the field current they have given me as 0.75 amperes. So this is actually very useful to me, right? Because they have given me Eg and they have given me the field current. So in the case part B, they have given me the field current If during maximum loading is 0.75 amperes, and they have given me the Eg maximum, right? Eg during the maximum loading is 160 volts. So If maximum is equals to what? It is Vt during the maximum. It is not the maximum value of Vt per se, but it is the value of Vt at maximum load. So that's why I am writing it Vt maximum divided by Rf, okay, is equals to 0.75, right? And Rf we have already calculated in the previous case, which is 125 ohms, correct? It is 125 ohms. We have already calculated it, right? Rf or Rsh, whichever one we say, does not matter. So Vt will be equals to, Vt maximum will be equals to 0.75 into 125. So Vt maximum comes out to be 933.75. So this graph, right? This graph will be further modified now. Vt maximum here, right, is 93.75 volts. So this is one of the answers. This is the part C, right? Part C we have already calculated. Part C. What about the part B? So part B is now very simple. I know what is the field current, correct? Can I find out the armature current? So my Vt will be equals to Eg minus Ia Ra. Very simple, right? I can easily find out my Vt here. Vt I know. Vt will be equals to 93.75 equals to Eg already they have given me, that is 160, minus Ia into Ra. Ia I don't know. I don't know what is the armature current. Ra I already know. Ra I have found out, that is 1.543. So 160 divided by 1.543. So the armature current comes out to be 42.936 amperes. So the, what will be the load current? Because I have to find out the IL max. IL max will be the extra additional current taken by the field. So it will be Ia max subtracted by If. So Ia max is 42.936 minus 0.75. So this comes out to be 42.186 amperes almost, okay, minus 0.75. So approximately it comes out to be 42.186 amperes. So this will be the answer, part B. Okay, so this question, trust me, you go anywhere, right? First of all, no one will take this question, and even if they do, something they will mess up. Okay, and I'm expecting one day if a difficult question gets framed from DC machines, these kind of questions will be asked. Okay, so these kind of questions, I will add the same question in test series, right? Ditto same question I will add in test series. Still, no one will be able to solve it because most of the guys, they just assume that they already know everything, so they don't watch the lectures, and without watching the lectures, they just attempt the test series, and they are not able to solve it. So that's the thing that I wanted to mention. Do watch the lectures diligently, because trust me, all this information is very important, because when a tough question will be framed, only you will be able to answer. No one else will be able to solve that. Okay, so yeah, I hope you have understood this uh, very basic point. Okay, so now let's move on. So this was a very good question. Now let's move on here. This is one of the answer, so mark the answers. This is one of the answers, right? And this is the last answer. Yeah, So now let's move on to the actual lecture. So we spent a bit of time here. So let's now move on to the actual lecture. So in this, let's discuss about the this characteristics. So one thing before starting, for series and compound, right? The problem is that the field winding, few part of the field winding is connected in series, right? So my IF is equals to IA, right? Compound also has a shunt winding as well, but so my field or flux is a function of load. If load changes, the flux also will change, right? So if load is connected, then flux will change. If load is not connected, of course we cannot operate our shunt machine in no load. We will never operate our shunt machine in no load. So we have to figure out a way so that I can make my flux to be constant if I want to plot the no load characteristics. Okay, if I want to plot the no load characteristics, how will I like plot for a series generator, right? That is what we want to understand. So generally for a series generator, we mainly discuss about load characteristics. Okay, no load characteristics we don't discuss, we convert it in separately excited, because if the flux is constant, only then we can discuss about no load characteristics. If the flux is not constant, we cannot discuss about that. Okay, so the voltage regulation of a series generator will be extremely poor. Why? The difference between no load and full load voltage is very high, making it unsuitable for constant voltage applications. We will see why is it the case. As the load current increases, the series field also increases, thereby strengthening the field flux, increasing the induced EMF. However, under no load condition, since there is minimal current through the field winding, the generated EMF is nearly zero. So voltage rises linearly with increasing load, leading to poor control over output voltage across load variation. So if the what happens at no load, right? If there is no load connected at the output, if IA is 0, then roughly my EG also tends to 0. So in no load there is 0 voltage. When IA increases, the flux increases, so my EG also increases. So with increasing voltage, with increasing load, the voltage is increasing, right? The generated voltage is increasing. So with increase in load, the flux is increasing, hence the generated voltage is increasing. So it's quite the opposite characteristics, right? Because we have seen, what we have seen till today is like when the current increases, the voltage, terminal voltage reduces, right? But it is quite the opposite. So its use case is quite different than normal generators. Okay, and why is it not used in no load? So no load characteristics, since the field winding is in series with the armature, under no load no current flows through the circuit, resulting in no excitation, thus no generation of EMF. Here you might have a doubt, sir, isn't there a residual flux here? Yes, there will be a residual flux here, which you are correct, but as right, it is no load, there is no load connected. So yeah, there will be some voltage developed that will be equals to E residual, that is fine, but IA will be 0, it will not supply any current, right? And there will not be any voltage buildup. So although it is no load, although I can say either there is no excitation or I can say there is some E residual, but if I draw the circuit in no load, right? If I draw the circuit in no load, so this is the circuit basically, it is E residual here, then I have the armature resistance RA, then I have the field winding RF, let's say, and it is no load, right? So my terminal voltage VT will be equals to E residual, and my IF is 0, and my IE is also 0, IL is also 0. So there is no possibility of voltage buildup. Previously what was happening, there was a positive feedback. So initially I had some E residual, due to that some IF current was flowing, IF current was non-zero, due to that there was some positive feedback, that is IF was increasing, hence the flux was increasing, hence the E residual was increasing, E induced was increasing, and it was a positive feedback. But here there is no possibility of positive feedback because my field current itself is 0. So there is no possibility because the field current and the armature current are in series with each other in case of no load, and there is no short circuit path. Previously it was shunt, so there was short circuit path, right? That is the difference, right? So how do I actually develop the open circuit characteristics? What we do to draw the open circuit characteristics at or no load characteristics, it must be temporarily converted into separately excited. Disconnect the series field windings from the armature circuit, connect the field windings to a separately DC source to excite the machine independently. Once the field current is made independent, the generator is run by a prime mover and the output voltage is recorded at various field current values. Okay, so basically its no load characteristics will be similar to series field to separately excited field one. Okay, two separately excited field one. So what I can say is that the no load characteristics will be same, because I know if I try to actually plot it, right, my IF is always equals to IA equals to IL. So actually, to be honest, here the load characteristics and the no load characteristics will be same, right? Because the load current and the field current are same. That's why we will only plot the load characteristics and that's it, right? We don't plot the no load characteristics. Okay. So no load characteristics, if you really want to plot for the machine, what you have to do, you simply have to open circuit the field terminals, and after open circuiting the field terminals, you directly uh, use it as a separately excited machine. Okay, so now let's discuss about the load characteristics. What will be the load characteristics? So the load characteristics, as I mentioned initially, it will have some E residual, right? Even if there is no field current, right? Field current and armature current are same. Even if there is no field current, there will be some residual flux, and as the load current increases, the field current increases. Hence the voltage also will increase. So it will just follow the magnetization curve. That's it. Okay. So this, right, is just following the BH curve. Okay. Now, so this also can be called as the no load characteristics as well. This also can be called as the no load characteristics. Okay, like both ways you can do. Either you can use it as separately excited, or this is same. This is same as the separately excited only, right? This characteristic is the same as the separately excited machine only. Okay. Yeah. Now, what about the load characteristics? So this is also known as the load characteristics only. So what is the external characteristics? So now I have not considered any drop. So this, right, if this is with respect to EG and IF, then it was no load characteristics, right? If let's say, let me mark it, this is EG. Now if I consider V, the terminal voltage. So what is the terminal voltage equals to? So the terminal voltage will be the voltage drop, that is E minus IA into RA plus RAC, right? So I have to consider the armature drop, right? I have to consider the armature drop. So that will give me the VT, correct? So that will give me the VT. So if I consider the armature drop, the graph will somewhat look like this. Okay, so this is the drop, this is the IA into RA into RSC. Okay. Now if I consider the armature reaction, right, I have to consider the armature reaction drop due to armature reaction. So further it will be dropped, okay, to the bottom. So there will be drop due to armature reaction as well. So actually first of all I should have told you that this drop is due to the armature reaction and this drop is due to the IRA drop, because if some load current is there, of course there will be some armature reaction. Okay, armature reaction. Okay, so yeah, this is the case over here. I hope you have understood this basic point. Now like this is the external characteristics. This last one is the external characteristics or load characteristics of a DC series machine. Okay, very simple and very easy to understand. I hope we don't have to understand this further. So this has the poorest voltage regulation from no load to full load, because like what is the voltage regulation formula? Voltage regulation is V no load minus V full load divided by the V full load, right? So voltage regulation is V no load minus V full load divided by V full load. I guess I also don't remember what is the, so this difference is very large, very large difference. But in case of other machines, right, the difference is not much higher. So that's why the voltage regulation is very high. Hence voltage regulation regulation is poor. Okay, that's why the voltage regulation is poor. So these are the few important things that you have to understand. So these characteristics represent the terminal voltage and load current. Since the field is in series, any change in load current immediately affects the field strength. The terminal voltage initially increases with current due to increasing flux, but starts drooping after a point of saturation and increase in internal voltage. So here, right, initially it will increase slightly, but of course it will start a bit of drooping because here the armature reaction will be much higher. The characteristics has a rising portion followed by drooping portion and typically lies below the internal characteristics due to internal losses and armature reaction. So this is known as the internal characteristics, and typically it will lie below it. Okay. So typically it is used as a booster generator. What do you mean by booster generator? So basically a booster generator basically means if let's say I have a generator here, and if the load current increases very high, then what happens? Then if I have terminal resistance, so I want to discuss about this. Let me take a practical scenario. Okay, so let us discuss that if the, let's say the generator, right, generates EG voltage, this voltage is almost constant, let's say 100 volts, and let's assume that the terminal resistance, transmission line resistance is 1 ohms. Okay, and let's assume that initially the load takes a current of 10 amperes. So if the load takes a current of 10 amperes, then what is the VT? VT is basically 90 volts, right? If I increase the load current to 20 amperes, so my VT will be equals to 80 volts. So now my terminal voltage reduces very high, right? It reduces very high. What if I want to boost this? So what we can do, we can connect a DC generator in series, DC series generator. So if the load current increases, right, now if the load current increases to 20 amperes, what will happen? It will provide additional. So here, right, we see that as the load current is increasing, so there is it is providing extra voltage. If the load current is 0, it is providing a constant voltage. Here, right, it is not providing any voltage, right? So that's why if initially at no load, this DC series generator will be of no use. But at full load, it will provide an additional voltage to nullify this voltage drop across the transmission line. But what is the problem? Problem is this DC generators needs energy. So someone has to supply the energy, right? The drop cannot just come from the sky. Someone has to do some work, right? So advantage is basically this series DC generator provides additional voltage to improve voltage regulation. And what I can say is, sorry, it is very sleepy now, but someone has to deliver mechanical power to the generator. So basically the key point is, so nothing comes for free, right? There is always a cost associated. Okay, there is always a cost associated. How much do you want to give, right? So that was about the use case. So they are used as booster generators in long transmission lines feeder to compensate the voltage drop. As current through the feeder increases, the voltage drop increases. A DC series generator placed in series in the feeder increases its outputs automatically with increase in load current. This helps compensate with voltage drop dynamically and maintains the voltage at the loop end. Okay, it helps in maintaining the voltage at the loop end. Okay, so series generators are rarely used alone for supplying power due to their poor voltage regulation. So they will never be used alone. They will always be used with a shunt generator. However, they are still useful as voltage boosters and current regulators in arc winding transformers, because it supplies high amount of current for low voltage. It can supply high current for low voltage. So that is also another advantage of series generators. Okay, so these are the few use cases. I hope you have understood this basic point. Now let's discuss about compound generators. So what will happen in compound generators? So in compound generators, what you have to understand is basically there are main funda is, sorry, in compound generators with a series field, a shunt field also will be added to improve the load behavior. So this hybrid usage is far more practical than just the series generator. So now my flux will be a combination of phi sh plus phi ac. So it does not only depend on the load as well, load current, it also depends on the terminal voltage. So yeah, so it becomes very interesting. Okay, so in case of compound generators, mainly there are three kinds of compound generators. Okay, one is like in case of voltage regulation, one is over compounded, level compound, under compounded. We'll discuss about this. So a compound generator combines the benefits of both series and shunt field windings. The dual excitation design allows better control over the terminal voltage. So first one is the cumulative DC generator. In case of cumulative DC generator, the series field flux adds to the shunt field flux. This results in improved voltage regulation with increased load. Okay, so if I see the cumulative compound generator, right, if I just draw the cumulative compound generator, in case of cumulative compound generator, this is the motor. So both the flux are in the same direction. Okay, this is the cumulative compound generator. So overall the flux is equals to phi sh plus phi se, right? If the so my phi series will be proportional to the load current, and we assume that the shunt, right, is almost constant. Okay, that the shunt flux is almost constant, because we assume that the terminal voltage will almost remain constant. Why? I will say that. Okay, so if the load current is now increased, right, then the armature current also will be increased, correct? Due to that, the series flux will be increased, right? So if the armature current is increased, what do I know? If the armature current is increased, what is my Vt is equals to Eg minus IARA. So the armature current increases, Vt will reduce. If Vt reduces, what will happen? The shunt flux will reduce, right? But what have I told you? The series flux will increase, correct? If series flux increases, what will happen? If series flux increases, that will just increase the Eg. If Eg increases, then the Vt also will be stabilized, Vt also will increase. Okay, so there are two ways in which this compensation can happen. All of it totally depends on the how much compensation the series winding will give, right? Because it all depends, because the series flux is increasing, so the Eg will increase. By how much the Eg increases, that depends whether the Vt will go lower or higher. So ultimately, right, what do I know? Ultimately, what is my phi series equals to? So basically, I am telling you phi series is proportional to IF, right? What is phi series exactly equals to? Phi series exactly is equals to MMF upon the reluctance, right? Reluctance is just a constant number. So what is the MMF? MMF is NSE, the number of turns in the series winding into the field current, right? It all depends that there are three cases. One is over compound, then we have level compound, then we have under compound. In all these three cases, it depends what is the number of turns. Okay, so in the first case, over compound means there is more compensation from the field windings. If the number of turns of the field windings is higher, so IF is IAC only, that is the armature current. If the number of turns is higher, so the flux will increase further, hence the Eg also will increase. So here in this case, this will be NAC1, that will be larger than the level compound. In the second case, the number of turns will be lower than the first case, because the compensation will not be that high. Still some compensation will be there, that is still some Eg increase will be there, but that will not be enough to increase over the previous voltage level. Okay, and this will be the under compound, where the compensation will not be enough. Basically the voltage will simply reduce. What do I mean by it? So basically, right, the characteristics, the load characteristics, open circuit characteristics is almost same only, because there is no load. It is just like acting like a shunt generator, but the load characteristics is the important one. So what I see is that if the IF and this is the Vt, so this is the no load voltage, initial no load voltage here. Okay, so if the enough flux compensation is there, then the voltage will slightly increase, right? So that is what, no, that is the characteristics of a over compounded machine. Okay, and if the number of turns is lower than the over compound, then the voltage compensation is not enough, that is the change in flux is not enough to increase the Eg generated voltage very high. So the terminal voltage is level compounded, so it will be a straight line parallel to the x axis. and if the compensation is even lower, flux compensation is even lower, so it will be lower. Okay, so what I can say, this will be over compound, that is NSE 1. This will be level compound NSE 2, and this will be the under compound, where the flux lines increase, series for flux lines increase will not be enough. Okay, so I hope you have understood this basic point. There is no need to go too much in depth here because they will not ask you much questions. Just the important part is the level compound has good voltage regulation, because even if there is some load variation, the terminal voltage is not changing. So this has good voltage regulation. Both, all these three only have good voltage regulation. Okay, voltage regulation or voltage, yeah, voltage regulation only, right? Yeah. Okay, so this was about the, so voltage regulation among all DC generator types, over compound is the best one, because in over compound, right, sorry, not level compound, sorry, over compound will be the best. Okay, level compound will be good voltage regulation, over compound will be the best voltage regulation, and the under compound will be the worst. Why? Very simple to understand, because with increasing load the voltage is reducing, so voltage is deteriorating, that's why it will have the worst voltage regulation. Over compound will have the best voltage regulation, because with increasing load the voltage does not deteriorate. Okay, and this is like good voltage regulation because voltage is not changing. Okay, all three are generally okay for like this voltage regulation only. Okay, so among all three, this over compound will be the best voltage regulation. Application commonly used where voltage needs to be stable or slightly increase with load, such as lighting load, distance DC transmission line, or heavy duty equipment. So these are used in these cases. The cumulatively compounded. So next one which we will discuss is the differentially compounded DC generator. In case of differentially compound DC generator, what will happen? Now in case of differentially compound DC generator, the important fact to note here is that my overall flux is a combination of the shunt flux minus the series flux. Shunt flux minus the series flux. Okay, so it is a difference of shunt flux minus the series flux. So what I can say is, again the same thing, right? Now things will change, like the voltage will reduce further. In this case the voltage will reduce further. So now if the load current increases, the what will happen? Basically, what is my VT? VT is equals to EG minus IA RA. So if load current increases, VT will reduce, right? If load current increases, the as my IF is same as IA, I series field current according along the series winding is same as the armature current, load current. So this will also increase, hence that will what? Increase the flux, but this time the flux is in opposing direction, right? So this time the flux is in opposing direction. So what will happen? So my generated EMF will reduce because the overall flux reduces, right? Because this is in the opposing direction. So my EG also reduces. So if EG reduces, so my voltage further reduces. So it is like a shunt DC machine, but even worse. Okay, like a shunt DC machine, but even worse. Okay, because here anyways the flux is reducing and the series field is further reducing it. The series field is further reducing it. So if I copy the previous graph, right? Copy the previous graph. So I will add the differentially compounded machine here. So over compound, level compound, all these are cumulatively compounded and differentially compounded will lie somewhere here. So it will be the words basically, something like this. Okay, this is the differential one. So this will be the worse than all of them. Okay. So where will shunt lie? Shunt will be bit better than this. So shunt, right, because it does not have this opposing flux. In case of shunt DC machine, I have only 5 SH. So shunt DC machine, the flux will be bit better than this. Shunt will be like this. Okay. So this will be the shunt. And how is the series? So series will be somewhat like this, because series is just opposite, because with increase in load the generated EMF in a series generator increases. Okay, these are the overall graphs. So understand each of them conceptually. Okay, understand each of them conceptually, what does each of them means. Okay, so one more thing here is that no, this is fine, yeah, all this is fine. So under no load condition, both cumulative and differential compound generators behave similarly, such as shunt, because no load condition, at no load what is happening, only the residual flux will be there, that is present in the shunt field winding. Okay, because in series field winding there is no current, only the residual flux will be there. That's why all these generators, cumulative, differential and shunt, all this will behave same at no load. So if you see, all these three are starting from the same point at no load, right? But after that it changes because the flux behavior changes. Application of differential compound generator are preferred, like arc welding, where short circuits are or sudden high currents are common. Their inherent voltage drop with current helps protect against damages during faults. So if I want even more protection, right, if there is inherent voltage drop, so the current I want to also drop sharply, then the differential compound generators can be used. Differential compound generators also can be used in case of arc welding process. In case of arc welding, where the current is high but voltage is low, because in case to generate arc, right, to generate arc, what happens in arc? So initially when you generate the arc, initially to generate arc, you need high voltage. Why? For breakdown of air. So basically if I have two plates here, right, and if I want to generate a arc here, right, this is a arc, so basically I will need high potential difference, HV, initially, just to initially generate the arc. Okay, so after generation, we need we don't need high voltage to maintain the arc. Okay, we don't need the high voltage to maintain the arc. Okay, only during the formation of arc. So only during formation of arc we need the high voltage. I am sorry for my handwriting. Formation of arc. Okay, this is property. So after that we don't need high voltage to maintain the arc, but we will, because a high current will pass through this, we will need high current. High currents will be required to maintain the arc. So that is done by the differentially compound generator, because if you see, voltage is reducing very sharply, but current is also increasing very sharply, right? Current is increasing very sharply. So this kind of property is given out by the differential compound generator. Okay, so that's why differential compound generator is generally used in this arc generation process. Okay, so this is the summary table: over compounded, level compound, under compound, what is the voltage drop, what are the use cases. So you can go through this can be theoretical questions. Okay, so yeah, that was it basically. So I hope you have understood this thing. So for another important point, for over compound and for series generator, the for over compound and series generator, generator, the voltage regulation will be negative. Okay, so basically it will be negative. That basically means that what is the voltage regulation formula? Voltage regulation formula is V no load minus V full load divided by V full load into into 100%, right? So of course the no load voltage is higher than the full load voltage for over compound and series. If you see, sorry, for over compound and series, right? For over compound, okay, no load voltage, yeah, no load voltage will be kind of lower. Sorry, no load voltage will be kind of lower than the over compound, right? For over compound, and for series also no load voltage will be lower than the full load voltage. That's why the voltage regulation will be negative. For all the other cases, voltage regulation will be positive. Okay, for all others, for others voltage regulation will be positive. Okay, so these are the graphs basically. If you see that this is the shunt, sorry, this is not the series. Okay, here, right, the numbering is wrong. So where is shunt is here. So this will be the fourth one, sorry, this will be the fourth one, that is the shunt one, and series one will be this one. This one will be the series one. Its no load voltage will be lower somewhere here. Okay, level compound, okay, this is not the level compound, right? What is this 3 one? I don't know. Level compound will be somewhat like this, right? Yeah, over compound is correct, series generator is correct. Level compound will be somewhat like this. It will be just straight line. This will be the level compound. Then we have shunt we have already done. Then we have under compound, sorry, over compound will be the top one, right? Because, yeah, sorry, over compound will be the top one, sorry, over compound, this will be the over compound, this will be the under compound. Separately excited, okay, separately excited will just, okay, it will the in, so the I'm here plotting the terminal voltage, right? For separately excited it will be just a linear graph, because for separately excited Vt is equals to Eg minus IaRa, because Eg is constant, right? For separately excited Eg is constant, so it behaves like shunt, but it will be more of a straight line, because Eg does not change at all. In case of shunt, Eg will change, right? So separately excited will be somewhat like this. Okay, then differentially compound generator. So differentially compound generator will be a steep fall. So differentially compound generator will be like this. Both of them will have same no load characteristics. Okay, one more thing, the shunt and this, right, should have same no load characteristics, right? So it will be somewhat like this. Separately excited will have lower drop than shunt, so it will be somewhere like this. Yeah, it will be somewhat like this. And the shunt will be somewhat like this. Yeah, and the differential will be even worse. So differential will be even worse, something like this. This will be the last one, that is seventh one. Okay, so these are all the graphs basically. I hope everything is clear with all the graphs. Okay, I hope you have understood this point regarding all the graphs. Okay, so yeah, so the most things are clear here, and I hope this can be asked in exam. Okay, this graphical representation, which graph represents which generator, this can be asked. So keep this in mind. This is the important portion, graphical understanding. Okay, now let's discuss about few questions. So I will pause the video, you try out few questions, and of course I will come back with the solutions of these questions. Okay, try out these questions. Okay, this answer is already there. This is the this question, we have a lot of questions to go through. Okay, so let's start with this question first. The external load characteristics of a DC generator operating at its rated speed is assumed to be linear. Okay, it is assumed to be linear, the external load characteristics. uh, if the load consists purely resistance and load current of 50 amperes, determine the resistance of the load circuit. Okay, this is the basically, this is what this is basically, they have told us this is the external characteristics. So it will be with respect to the terminal voltage, right? This is the terminal voltage Vt. So I know that the load consists purely resistive and the load current is 50 amperes. Okay, I don't know the field current, but from here, right, what is this equation? I know what is the Vt if we assume that it is operating at rated speed, and the external load characteristics is almost linear. That means what? That means it follows the equation of line. Vt will be equals to Eg minus IaRa. That's it, right? Because Eg is assumed to be constant, because they have not mentioned anything, so I will assume Eg to be constant, right? They have not mentioned whether it is flux or something, right? So from here I can easily find out the values, right? So I observe if the load current is 0, IL is 0, then what is the uh, value of Vt? So if Ia is 0, the terminal voltage is 100. Now if the here the voltage is 90, then the current is 100 amperes. So what I can say is, what is Eg? So at no load, so as we have to assume, unfortunately it is a separately excited machine, because they have not mentioned anything, right? So assume the machine, assume the generator to be separately excited. Assume the DC generator to be separately excited at no load. Okay, assume the DC generator to be separately excited at no load. Then at no load, what will happen? At no load, if it is separately excited, then I don't have to worry about the field current. Then my Ia will be equals to IL. If it is separately excited, if I draw the circuit diagram of a separately excited machine, I don't have to worry about the field current, right? Simply my load current will be same as Ia, right? So at no load, Ia equals to IL equals to 0. Hence Vt terminal voltage will be Eg. So I can see the no load voltage or Eg is 100 volts. So from here I can get the information about Eg. Eg is 100 volts. Now what more do I know? I know this equation at IL equals to 100 amperes, the Vt is 90 volts, right? So I can plug in the values in this equation. I can plug in the values in this equation, right? So Vt is 90, 90 equals to Eg minus IL or Ia into Ra. Ra value I have to find out. So Ra from here I can easily derive. It will be 10 divided by 100, that is 1 by 10 ohms. Okay, so this is my resistance value. From here I am able to find Ra. Now what are they asking? They are asking what is the load resistance, right? If the load is taking a current of 50 amperes. So what is the term, like what, how do I find out the load resistance? So load resistance RL will be the voltage across the load, because it is a purely resistive load. It will be VL upon IL, right? VL upon IL, purely resistive load, it will be VL upon IL. So I have to find out VL. VL is VT, and what is IL? IL is IA. So I have to find out the armature voltage and the the terminal voltage and the armature current, right? So what will be the terminal voltage? VT is equals to EG minus IA into Ra, that is 0.1. So EG is 100 volt minus Ia into 0.1. Okay, so so load current they have mentioned is 50, right? So IL I already know, they have mentioned is 50 amperes, because already they have told me, right? The load is taking 50 amperes of current. Load is taking 50 amperes of current. So from here I can easily find out the value of Vt. So Vt will be 100 minus 5, that is equals to 95 volts. So my resistance RL resistance will be Vt, that is 95, divided by armature load current, that is 50. So from here I can easily find out the value of the load resistance, that will be 95 divided by 50, it will be 1.9 ohms. This will be the answer. So these kind of easy KVL KCL questions can come, and graphical questions also can come, right? Let's do this next question. A cumulatively compound DC generator is delivering 20 amperes at 200 volts terminal voltage. So Vt is 200 volts and the current it is delivering 20 amperes. Okay, it is cumulatively compound delivering, so IL is 20 amperes, and it is a DC generator. It is cumulatively compound. Okay, if the series field winding is suddenly short circuited, so if I suddenly short circuit the series field winding, what will be the resulting terminal voltage? So in a case of cumulatively compound generator, I know that phi is equals to phi s plus phi ac. So if the field winding is suddenly short circuited, that means like here is the field winding, and if I short circuit the field winding, right, whatever current was flowing through here, none of it will flow through, right? It will be zero. All current will flow through here, because the voltage across the field winding will be zero. So this will be simply zero. So my overall flux reduces. If my overall flux reduces, my Eg will reduce. If Eg reduces, the terminal voltage also will reduce. So it will drop below 200 volts. Okay, it will not rise. It will increase to 220 volts. I cannot comment. It will remain unchanged. No, it will drop below 200 volts. So option D will be the correct answer in this question. Let's now solve the next one. So in next one, a compound DC generator. So again I have a compound DC generator. They have not mentioned whether it is differential or cumulative. So I have a DC generator that is compound, is supplying full load current at terminal voltage. So IL is IL rated and supplying at terminal voltage Vt, that is 230 volts. Okay. If series field winding again is short circuited, what will be the resulting voltage if the terminal voltage increases beyond the generator is overcompounded? So if it increases beyond 230 volts, what does it mean? Is it overcompounded? Yes, it is correct, because in case of overcompounded, I am overcompensating it, right? N series number of turns is very high and it is cumulative compound, so phi will be, sorry, if the terminal voltage increases, if the, okay, if the field winding suddenly gets short circuited, okay, sorry, if the field winding suddenly gets short circuited, I cannot comment, right? If the field winding suddenly gets short circuited, if it is over compounded, then what will happen? This will simply be 0. So that means my flux will reduce, so overall the induced EMF will reduce, the voltage will not increase, actually, sorry, the voltage will not increase, so this is not correct. If the terminal voltage increases beyond 230 volts, the generator is differentially compounded. Is this statement correct? So for the second statement, this was for the first statement. For the second statement, if it is differentially compounded, what is the resultant flux? The resultant flux, right, is phi sh minus phi ac. Okay, resultant flux is phi sh minus phi ac. So if suddenly it is short circuited, what will happen? The field current will be 0, right? Because the voltage across the field windings will be 0, hence no current will be flowing through here, all the current will be flowing through the short circuit path, so this will go to 0. So my flux will increase, so my Eg will increase, so my V also will increase. So this is actually absolutely correct, that if it is differentially compounded, the terminal voltage will go beyond the previous voltage 230 volts. If the terminal voltage drops below 230 volts, the generator is differentially compounded. Wrong. Already, sorry, this is fourth statement is wrong, this fourth statement is not correct. Okay, let's read this. If the terminal voltage drops below 230 volt, the generator is over compounded. Correct. As discussed here, the flux will reduce, because this will go to 0, overall flux will reduce. So if flux reduces, my Eg also will reduce, hence my Vt also will reduce. Okay, so this third statement also is correct. If the terminal voltage drops below 230 volts, the generator is level compounded. This is also correct, because for level compounded as well, it is cumulatively compounded, so this flux equation will not change. Okay, so anyways this flux will go to 0, so anyways the voltage will drop only. So here 2, 3 and 5 are correct, so option B will be the correct answer for this question. Option B will be the correct answer for this question. Okay, let's do the next question. So like kind of same kind of question only. A compound generator is operating cumulative mode. A generated voltage is this. What is the impact if the series winding is suddenly, okay, this is the same question, right? Okay, this right, what will happen in this case? The voltage, it is a cumulatively compound, so terminal voltage will reduce, so terminal voltage will go below 220 volts. This we have already discussed, right? Now what happens in a differentially compound generator? What would be the effect if the shunt field winding is open circuited? If the shunt field winding is open circuited, then what will happen? So in case of differentially compound, right, generally we assume, also they should have mentioned here, they should have mentioned that shunt field is dominating, should have been mentioned here. So if I assume shunt field to be dominating, what is the resultant flux for a differentially compound generator? It is phi sh minus phi ac. Now if suddenly the shunt field is open circuited, that basically means ISH, right, will be 0. That means phi sh will be 0. That means my phi will change to minus of phi ac. So flux direction has reversed. Okay, so basically what will happen? The Vt will change its polarity. Vt will change its polarity and it will deliver also in the other current. So Vt and Ia also will change its polarity. Both will change its polarity. Why? Because I know that torque is proportional to flux Ia, right? If torque, like I'm providing the torque to the generator, so direction of rotation is same, the flux direction has changed, so Ia also will change to make the torque direction same, right? So both Ia and Vt will change its polarity, will change its direction, right? So Eg also, basically Eg will reverse its direction, Eg, Vt, Ia, all these will reverse its direction. Okay, so yeah, same thing is written over here. This we already had discussed. Okay, this is for the compound generator that we already discussed. I don't think we need to add this over here. Okay, the internal characteristics of a DC generator represents the relationship between the generated voltage and the armature current, right, or the load current, sorry, the generated voltage or the armature current or the load current, right? So it represents the armature current and the generated voltage accounting for armature reaction. Yes, it is correct. So because you have to account for armature reaction as well. Armature reaction, why does it happen? Because my armature current is not equal to 0. Okay, field current and no load voltage, no, this is the no load or open circuit characteristics. Field current and generated voltage under load conditions, armature current and terminal voltage output. Okay, so no, this is not correct. Armature current and terminal voltage, this is the external characteristics. Actually even armature current we don't do, right? Actually, like they say armature current, but it is almost equals to the load current only. Okay, we can write like one thing also, if they tell you that your internal characteristics, right, it can be with respect to armature current as well, no problem with that. So internal characteristics, right, mainly generally we discuss about with respect to the generated voltage Eg versus the load current, but sometimes they can give this with respect to Ia as well. Sometimes they can give this with respect to Ia as well, right? Okay, same for the external characteristics. So for external characteristics, we'll have the terminal voltage versus the load current, or sometimes they discuss with respect to Ia as well, right? Okay, because it is roughly the same. For a shunt machine, it is roughly the same because If is assumed to be roughly constant. Okay, which type of generator is not suitable for parallel operation? So uh, uh, so here, right, all these three, series generator is not suitable, compound generator is not suitable, only shunt is suitable. Why? Because if I show you the characteristics, actually compound generator is also suitable, but here they have not mentioned what kind of compound generator, right? If it is a differential, I don't know, so I cannot include everything, right? So they should have mentioned cumulatively compound are suitable, but differential compound are not suitable. So compound generator, right, differential not suitable, because if you see in case of differential, right, with a load variation there is huge voltage difference in case of differential. Okay, so let me just bring this as well, this numbering as well, right, otherwise you will be confused. So in case of differential, if we see the seventh one, there is huge voltage variation with load variation, right? In case of series, if you see, there is huge voltage variation with respect to load variation. So I cannot use those in parallel. In parallel, voltage must be constant. So in case of shunt, if I see, like separately excited is the best one, separately excited, but they are not present in the options, right? Separately excited is best. After that, shunt. Okay, because if you see separately excited has very less voltage drop, right, it is almost constant with load variations, but shunt, if you see, also has very wide range, it has lower voltage drop. And compound generators are actually suitable, but differential is not suitable, that's why I cannot include compound generator to be my answer. Shunt will be the answer out of the following options. Okay, so yeah, this is the next question. Four types of DC generator operating at constant speed are listed here in list 1. Their corresponding external characteristics are given in list 2. match the list 1 with their characteristics in list 2. Okay, so separately excited will be the second one, because here the like voltage drop will be almost linear. So separately excited will be the second one. Series excited will be the one whose no load voltage is lower and full load voltage is higher. So this will go to the fourth one. Sorry, this is the separately excited. Shunt excited will be this one, right? This we already know, already have discussed. So this will be the first one. Over compounded will be the one in which the voltage actually should, okay, no load voltage again is lower than the full load voltage. So this will be the over compounded one, right? Because it has higher number of turns. So with increase in load, the generated voltage will further increase because the series winding turns is further higher. Okay. So here the D will be with option C. Okay. Oh, okay. Okay. One more thing I forgot to tell you, that we don't run our machine in no load for series. Okay. Actually, both of these will work. Okay, one slight mistake. Actually, they should have mentioned this. Actually, this graph should have been starting from the same point. So as these graphs are starting from the same point, so this will be for the compound generator, because for a compound generator the no load characteristics, like when the armature current is 0, the voltage is same, right? So we have to swap the numbers here. I was mistaken here. So series, like both of these cases, the no load voltage, not the no load exactly, the low load voltage, light load voltage and the full load voltage, like the full load voltage is higher than the light load voltage, right? So both of them can be of series generator or compound generator. But for this one, I see that the no load characteristics, when the armature current is 0, both of them produce the same voltage in case of shunt, and in case of over compound that is possible. So that's why the fourth one will be the over compound one, and the third one will be the series one. Okay, just be careful regarding this mistake. Okay, where are the options? Okay, options are not present. Okay, I'm sorry, there should have been options here. So like the options are not present, so you can do it by yourself, that my A will match to 2, my B will match to 3, my C will match to 1, my D will match to 4. So this will be the answer key: A2, B3, C1, D4. Okay, so that's it basically with the characteristics of DC generator. Now we will discuss about the characteristics of DC motor. So I hope you have enjoyed this lecture. If you did, make sure to hit the like button, make sure to comment on the video, and I will see you in the next video. Until then, happy learning.